Hi all, I'm in a different classroom this week and I've got a little bit different setup here. So hopefully this works just as well, if not better, than the previous weeks. So in this video, I want to pick up where we left off with our ideas about regression and the slope coefficients in our models. And I want to hit on the important parts of Chapter 2. And hopefully you're getting more comfortable with doing things in R and looking at that R output and being able to say some more things that I've been requesting in the activities and with the challenge sheet. But hopefully this will round out the whole picture of what you need to talk about when you interpret a regression and what's going on with it. So I just want to hit on some of the big ideas from Chapter 2 and also tell you what not to pay attention to in there. And that should be it. So let's pick up where we left off with a really basic model. Chapter 2 is all about inference with regression. And remember that inference is taking something from a sample so that we can say something about a population. Inference, in what you've seen before in your typical statistics classes, has been using t-statistics or maybe a randomization distribution and getting a p-value and talking about significant results or significant differences. So statistical significance is the same thing with regression, but now we're just looking at particular things within our regression to say whether or not they are statistically significant. So let's start with sort of the example that we've been working with a little bit here. And as you can see, I've written out the theoretical model for what is becoming our housing data, our housing situation. So I want to predict the price of houses using square feet. And square feet, as you see, has its slope coefficient, which we learned about last week, and my model has an intercept coefficient as well. So as you can tell, I have an error term and there are no hats on anything. So this is my theoretical population model that describes what's out in the universe and what I'm trying to get to. So if I, for example, I'm just going to make up some numbers here. So let's say I run some data and I get some result in R that gives me some model for price of a house. And let's just say that the intercept is $10,000. And let's say that the slope coefficient here is, we'll just say $1,000 times our variable, explanatory variable square feet. Okay, so I just made these numbers up for example. And we know from our interpretation that, well, we can say that for every square foot increase in the housing size, we expect an average price increase of $1,000. So that's great. But here's the thing, is that statistically significant? This goes all the way back to our initial intuitions, I should say, when we're talking about whether or not what we observe in the data is statistically significant. So what does that mean for regression? Well, what this means and what we're asking is beta 1 statistically significant? Which is equivalent to asking, does square feet predict price with significance? So these are just our usual ideas about significance. Well, naturally, when we do this, we need a null hypothesis of some kind. And so I'm going to erase this to save space and write out sort of what we're working with here in terms of a null hypothesis. As you might be able to guess for a null hypothesis, on just this variable here, we're going to start and say that beta 1 is equal to 0. That's our null hypothesis. Our null hypothesis is saying that the impact of square feet on price is 0. Because what happens when I put in a 0 for my slope coefficient? Then this whole thing goes away. And I'm just left with price equal to some single number, which I'll get to in a second. So our null hypothesis for every slope coefficient ever is that it's equal to 0, that there's no relationship at all between square feet and price. Naturally, our alternative hypothesis is that the slope coefficient is not equal to 0. That there is some value here. That whatever it is, whether it's -5 or 1,000 or 1,000,000, that this slope coefficient, this beta 1, whatever is here, is not equal to 0. And then we have a model. So that's pretty straightforward, but I want to actually draw your attention to what this means in a deeper way. And the book doesn't necessarily talk about this, but I think this is really helpful. In words, what this null hypothesis is saying is that, make sure I get my wording right here, is that the model is no better than using the average price for every house. So again, what our null hypothesis is saying, and I'll show it on a graph in a second, is that the model is no better than using the average price for every house. And let's connect why. So let's plug a 0 in for beta 1 up here. Let's assume the null hypothesis is true and that there's no relationship between square feet and price, and I plug in a 0. So if a 0 is true, then my model becomes price is equal to some beta 0 plus 0. What it's telling me then is that at every single square feet, the predicted price for my house is just going to be this intercept. The way this works graphically is that, let's say we have 5 data points here, and I have square feet down here, and I have housing price up here. And let's say I put in the average value as a dotted line and say this is the average price of a house. Call it Y bar right through here. A slope coefficient of 0 is a straight horizontal line. And so what that's telling me is that if the null hypothesis is true, then my model is just one value, the average housing price, which will be this intercept beta 0. So what our model does is says, hey, I'm going to say that the slope coefficient is not equal to 0, and that actually I have a model that's better than just saying the average price for every house is going to be this one value. Instead, I'm going to say that beta 1 is not 0, and that I'm actually going to have some slope here. So let me clear this out. So if the alternative hypothesis is true, and instead, I know that my housing price is going to change depending on which square feet I'm at. And what it is saying is that depending on which square feet I'm at, the predicted average value is going to change. So for a house at, say, 10 or 100 square feet, that is going to have some average price. For a house at just, say, 1,000 square feet, that is going to have a different average price, going all the way up. So this is really fundamental because whenever we make a regression model with an explanatory variable, what we're saying is that I'm going to start from the assumption that every single house in my data set has the same average price, but then I'm going to test that by making a model and to seeing if I can show that the mean housing price is different at different square feet. And how we decide that is with what you've hopefully seen before. And that's a t-statistic. And that's given to you in your regression output. And it's defined as the value for the slope coefficient divided by its standard error. And all that's given in the table. And it gives you a t-statistic. All these parts are given to you in your regression output. And this works exactly the same as your usual inferential statistics because you are given a p-value. And we can set the usual significance level that we like, alpha equal to 0.05. So again, all we're doing is saying, for all the houses in my data, do they all have the same average price, which is just the average of the prices? Or does that average change depending on which square feet I'm at? And that's all a regression model tests. So if this model here were statistically significant, price equals 10,000 plus 1,000 times square feet, then I know that the housing price in my population is supposed to change. The mean housing price in my population is supposed to change with changes in square feet. One other thing about this before I clear all this away. Just a reminder what the standard error is. Remember, a standard error is due to sampling variability. So if I were to get another set of data and run a whole model again and calculate another slope coefficient, would I expect to get the exact same slope coefficient of 1,000? Or if I did it a third time, or I went out in a fourth time, or a fifth time, would I always expect to get 1,000 as my slope coefficient? No, because there's sampling variability, there's randomness, there are all kinds of factors that cause this slope coefficient to vary depending on which sample I'm looking at. And we measure that sampling variability with the standard error. So the standard error is just saying how much I expect my slope coefficient to change over repeated samples. The trick is that we want the actual value of the slope coefficient to be a lot larger than its error. That's all statistical significance measures, is the magnitude of something we're measuring divided by its error. And we're going to see that over and over again. So if the ratio is big enough, then we get a statistically significant t-statistic and p-value. If this ratio is too small, if our error is just much too big relative to the thing we're measuring, then we're going to get a small t-statistic and a large p-value and not find statistical significance. A lot of this hopefully sounds like review. I'm just hammering it into our situation with regression because we will see this over and over again. Okay. So let me put up just a little bit more with wording, and then that'll be it for this first part. In one racing, if you're sitting there and thinking and waiting and hoping that I would hurry up, just think about what would happen maybe if you added more explanatory variables to your model, and how that situation might start to change. We'll get to that in future weeks, but we're doing everything with one variable right now. So try to think about what adding on extra variables might start to do with things. So if the p-value on our slope coefficient is, we'll just say less than 0.05, that tends to be the case, then we reject our null hypothesis and we say, and we find evidence that, say, square feet significantly predicts price. Pretty straightforward. And if p is greater than 0.05, then we say we do not reject H0 and we do not find evidence that square feet predicts price. You can phrase this all kinds of ways. You could say that if p is less than 0.05, we reject H0 and we find evidence that beta 1 is not equal to 0, that beta 1 is statistically significant. So there are many ways to phrase this, and it's your choice, as long as you just communicate the idea that either our explanatory variable or our slope coefficient are statistically significant at predicting price. And I will repeat this over and over and over again, but remember, our model is about predicting averages. We start from the assumption that every single house has the same price, whatever the average sample mean price is for our data. And then our model changes that and says, well, what if it's not the same average price for every house? What if that average price changes depending on how many square feet we're at? That's what inference in this case is all about. So that's it for this video. And in the next video, we'll talk about some overall model measures to do more inference and describe more things. Great.